Good morning. As we open up today's lesson, I want to deal with a little situation that was asked about last year. And last year, when I introduced waves, we talked about a wave pulse, an individual wave chunk, and then versus a wave train, which is many pulses together. And someone said, Harmon, how do you measure a wavelength on something that only has one crest? And that person's absolutely right. It's very difficult to talk about a wavelength for this thing. There are advanced physics topics that talk about looking at the shape of this and saying what larger cosine or sine wave would this be a part of? But that's way beyond what we're going to do in this course. So wavelength and frequency only apply to wave trains, where you can easily measure the distance between two successive crests or troughs or whatever you got to find the wavelength. Today we're going to talk about interference, and I don't like this word, but it's the one that's used. Interference. Wave interference. Let's put wave up here. And the reason I don't like this word is that it really misleads you as to what's going on. Interference in most sports usually means that something has happened to the play and the game has been disrupted. You have to stop and reset, maybe some sort of throw in or take the play back to the original line of scrimmage or something like that. Interference means that there's been an interruption and two things have interacted in an inappropriate way. Wave interference is completely the opposite. I prefer the term superposition. That is to say, when two waves are in the same place at the same time. Almost had an ASB moment there. That's where you run out of room at the end of your page and you have to cram the last word up. That's my. Forgive me if you're in ASB, but the making of posters, when you guys have to make a lot of posters at one time, sometimes you see some people not planning out where the words go. I get a big kick out of that. So I like to teach about superposition / wave interference by discussing a situation, and this situation is called wave wars. So, wave wars. Let's just pretend that you and a friend are bored to tears, and so you're in the backyard, and between the two of you, you have stretched a rope out like this. And what happens is, oh boy, hold on a second. We've got gardeners outside. This is going to be exciting. What happens is one of you decides to shake a wave pulse towards the other person. You know what I'm going to do? I'm going to stop drawing the people here. And that wave pulse goes screaming towards your friend. And your friend decides at the same time to send a wave pulse towards you. So the big question is, what's going to happen when these two wave pulses meet? They're going to meet in the middle somewhere. They're probably both going the same speed, since the speed of a wave depends only on the medium. And what's going to happen when they meet in the middle? Well, what's going to happen is this is an upwards disturbance of the medium. This is an upwards disturbance of the medium. And so what we're going to get is we're going to get an extra tall upwards disturbance of the medium temporarily. Like if this was 1 and this was 1 in amplitude, this would be a 2 in amplitude. And then what happens after that? Do they bounce off each other? Do they pass through each other? Well, what you see is this. You see one hump here and one hump here. They're both an amplitude of 1, and they are moving on their merry way. So this is something we call constructive interference. And the reason is that these two have added together and made a pulse that is temporarily larger than either of the two of them. But from this experiment, it's unclear to see whether these two pulses bounced off each other or whether they passed through each other. So what happens is you decide to throw a 2-height pulse towards your friend, who is only throwing a 1-height pulse towards you. And now when these two combine in the middle, you're going to get a really large pulse of height 3. But now we're going to be able to sort out what happens, and after that, what happens is the smaller pulse continues on, and the larger pulse continues on this way. So now it's pretty clear that the waves pass through each other. I used to say waves pass through unmolested. I don't know why kids think that's so funny. I mean that they're unadjusted, unchanged. So maybe this is not the right word. Unchanged. In other words, the weird thing about waves is they can have a collision and then they are completely unaffected by the collision. Let's answer some other question in these wave wars here. Let's do something else. Let me get another piece of paper. Let's assume, for the sake of argument, that your friend decides to be crafty and clever, and you throw your 2 height pulse at him or her again, but she throws a -1 height pulse at you. What's going to happen when these two pulses get together? Well, they're going to meet in the middle, and the negative amplitude of the right-hand pulse is going to take away from the positive amplitude of the left-hand pulse, and you're going to wind up with just a small little 1 height pulse. And then, of course, these two things are going to pass through each other like this, continuing on this way, continuing on that way. So this is what we call destructive interference. And in fact, you can do this to a much more enjoyable degree if you were to shake a 1 height pulse and your friend was to shake a -1 height pulse towards each other. What would happen when these two got together? Well, they would exactly cancel out just for a moment in the middle, and then they would pass through each other. And this is called completely destructive interference. This kind of thing in the world of sound is actually the goal of the Bose noise canceling headphones, or any noise canceling headphones. In fact, we don't even have to talk about noise canceling headphones. Your cell phone has a main microphone where it receives the sound of your voice, but it has a number of other openings around the cell phone case where there are other microphones that are listening for the ambient noise. And what they do is they take your voice, which includes the let's call this one your voice plus the sound of the room and chatter around you, and they add to it an inverse copy of the other microphones, which are mainly picking up the chatter around you. That has the effect of seriously reducing the amount of noise and pickup from the noise around you, which is why, honestly, you don't have to shout into a cell phone most of the time, particularly those dangly headphone ones that have the little knob that sits by your throat or something like that, and you think that's just a volume control. That's where the microphone is, and it's got 2 holes on it, one on one side, one on the other, and it does this kind of destructive interference between those 2 microphones in order to eliminate a lot of the ambient noise. So you just don't have to shout or pick the thing up and put it right in front of your mouth. It works very well. So one more thing that we could talk about, and this is related to wave wars, and that is reflection of waves. Ooh, there's some sort of debris under here. Yeah, that's part of my breakfast. Sorry. Reflection of waves. So, what happens when a wave meets a boundary? And so let's just say that you are you're alone in the backyard. Your friend did not come over today. There's been an additional quarantine, and you decide to go ahead and tie the rope to a tree that you have in your backyard. And yes, I know that looks like broccoli, but it's a tree in Harmon drawing style. Okay, so you decide to tie the rope to the tree, and you decide to have wave wars with the tree. Well, you can't really do much except that you could shake a pulse and it'll scream along, and head towards the trunk of the tree. What's going to happen when this pulse gets to the tree? Well, as it turns out, it will reflect back at you, but it will come back. I suppose I should put the rest of the tree in there. It will come back as an inverted reflection. Inverted reflection. In other words, a 1 height pulse comes back as a minus 1 height pulse. This has a lot to do with the conservation of energy and the boundary conditions. This happens because it is a fixed boundary. So waves come back from a fixed boundary in a inverted sense. And that's interesting because if you were to send another wave, let's just say that as this wave was coming back, you had sent another wave towards this one, then you would find that these would have destructive interference. So you can still play wave wars by sending the first wave, and so that it comes back as if your friend had sent a wave, and then you can send the second wave and still have your fun. Now, this is a fixed boundary, and that gives you the idea that there might be other kinds of boundaries. Oh my, I'm looking at this picture, and all my broccoli has come together. What other kind of boundary could there be? Well, there is such a thing as a free boundary. Now, in the case of tying a string to something, the only free boundary I can think of is to take a very, very smooth pole, like a metal pole that you might have a chain link fence hooked up to, and then put a metal ring around it. And this ring is free to slide up and down. Now, if you would tie the rope to the ring, when the pulse gets there, this ring can go zing zing up and down, and that is not a fixed boundary like when you tie a knot around a tree. This is a free boundary, and you find that what happens here is that the pulse comes back at you, only now it's not inverted. It is an upright reflection. And so you could play wave wars that way with your free boundary. You could send another pulse as that one was coming back, and you could have all the different things that we talked about. You just need a different kind of boundary. Now, so understanding the boundary conditions can let you know what kind of reflection you're going to get. People have asked me, other than putting a ring around this, can you think of any other examples of a free boundary? Well, the edge of a swimming pool is a free boundary for water. So now if you imagine that we have some water and we have some water waves, the water touches the edge of the swimming pool, but it is free to go up and down. So if you send it a big cannonball splash on top of this thing, like let's make this wave really big, and you sent that in, it would come back as a mound of water. And you can go out into your pool or next time you go to a pool and you can demonstrate this. Now, I don't know if any of you have had experience with a waveless pool or perhaps a pool that has an infinity edge. Those pools have a different kind of setup. I don't know if I have room to draw this. Let's get the black pen down here in the bottom corner. What they have is they have a curb. The water comes right up to the curb, and then behind the curb is a trough that will collect the water and pump it back into the pool. So if a wave was to come along here, the wave would simply go over the edge and drop into the trough. Now, the infinity edge pool, they hide this wall behind so that it looks like the water goes off into the sunset. It's a really nice architectural look. I imagine some of you have that, although the effect is a little spoiled when you have a giant block wall behind you. But in Olympic swimming pools and things where people are splashing around in all kinds of different lanes and you don't want waves going back and forth, then they put these kinds of edges on the pool, and they're kind of nice. They're kind of interesting. It's a great engineering solution to a problem of waves. Okay, so there's our short lesson for today. There is one more topic we need to talk about, and that is the topic of standing waves, how you can make these waves plus their reflections fit into certain areas, like put a boundary on each side, like put a tree on each side and start shaking it and you get waves that fit. And there's a lot of phenomenon in physics that occur because of standing waves. If you've ever heard a tuned exhaust on a motorcycle or car, usually they're tuned to sound aggressive, and that what they do is they make it so that certain wavelengths, certain frequencies of the sound are reinforced by having a good standing wave. And we'll talk about that tomorrow, and that's very brief. You have most of the information you need right now to do the homework that I've asked you to do, so get cracking on that. And that one does need to be submitted. Don't really care how you submit your answers. For those of you who felt like you had to email something to me, most of the people who emailed me, your original submission actually went through on Google Classroom. So instead of emailing me an additional submission, why don't we have you email me and have me check to see if I got your original submission? So we'll get to the bottom of the technical details on this. Anyway, thank you for your attention.